Hello again. This lesson is called the sugar cube investigation. In this investigation, students predict, explain, and observe as to what will happen when sugar cubes are added to a vial or graduated cylinder of water. Now, in this lesson, students will be required to use some measurement tools, such as this digital scale that we have here. They will be making predictions about the total mass of the system or the objects that they are combining, right? And then will observe what happens to determine if their predictions are correct, and will use a model to explain whether or not their predictions were correct and why, based on the observations and evidence that they gather. Now, to start this lesson, students will need to weigh two matter systems, if you will. They'll have to weigh the cylinder that's full of water and record that weight as it is, because all of the matter will be combined into this particular container. So in this case, I'm getting 54.3 grams. And then when they weigh their sugar cubes, I recommend giving pairs of students 4 sugar cubes. And I recommend them receiving the sugar cubes or gathering the sugar cubes in a small cup to measure on the scale. This allows us to do one of two things. It allows us to measure them all together and then add them, or it allows you to measure the total weight of the sugar cubes and the cup, add the sugar cubes, and then subtract the weight of the cup, giving them the overall weight of the sugar cubes themselves. However you choose to do that is up to you. You can even introduce students to tairing or zeroing a scale if you so choose. So we are going to combine. Oh, hold on, almost forgot. Getting a 12.4 reading grams for the cup and cubes. Now we'll get these in here. Whoop. There they go. They didn't lose too much matter there. Now again, one of the key things that we're exploring and thinking about here is not only the process of dissolving, but also this idea of mass being conserved, especially when matter all of a sudden starts to disappear, so to speak. And students can help speed along this process by shaking up their now solution. All right. Students will observe small particles in the water. Right. They'll also observe that those 4 cubes have gotten considerably smaller. One thing I like to do is actually allow it to sit for a minute and have students observe first the cubes. They'll actually see the cubes crumbling away over time. Right? But if you shake this for long enough, ultimately those cubes will almost completely disappear, or there will only be a small amount of powdery substance at the bottom. Now I'm receiving a total here of 63.4 grams. This is considerably less than what I had if I were to add those 2 weights together previously. But let's not forget that we need to include the cup if we use that during our weight of the sugar cubes. In this case, I'm now getting a reading of 66.6 grams, which is 0.1 off of our total weight. This is something that you are going to have to reconcile with your students through some conversation. Where did that 0.1 gram go? Does the 0.1 gram difference account for the complete disappearance of the sugar cubes? Or could something have happened? Like maybe our scale wasn't correctly tiered between one group or another. Or maybe when I dropped those sugar cubes, some of those particles may not have made it into the container. These are some of the errors that students may have to discuss in order to reconcile their data with the big understanding that we want to walk away with, that matter is conserved in a closed system or a closed container.
When students turn to their sugar and water mixture investigation notebook page, they're presented with a space for a photograph or diagram before the matter has been mixed, as well as a table where they should write in the mass in grams of those two components of the mixture, that is the water and container and the cubes and the cup. The everything after combining will be filled in when we get a final total amount by combining them. Before we do that though, we want to make sure that students complete this section. A prediction about what will happen to these two sets of matter when the matters are combined. Now, students who aren't really sure what you're looking for here ask, what will the cubes look like? Will they keep their shape? Right? Or do you think something else will happen to them? What will happen to the height of the water when we add these cubes in? Right? And why do they think that will be the case? You may also want to hit in here a prediction about what will happen to the mass of the mixture. And for some students or your class, you may want to prompt them with the mass of the mixture will increase, decrease, or stay the same, and allow them to debate between one another or support reasons for why they think one or the other. After the matter has been mixed, students will once again want to record the visual evidence of what has happened. In my model here, I have demonstrated that the mixture has become slightly opaque. I can see little things sort of floating around in there. As some students will see, they might have some pieces that appear to have sunk to the bottom and sort of collected down there if they haven't shaken it vigorously enough, or haven't fully dissolved all those sugar cubes. What they will not see are those 4 big cubes sitting in the container. And we'll want our students to determine if their predictions were correct or incorrect by circling those and writing any observations that they shared as a pair or as a community here in this space. This page in the student notebook is here for the graphing portion of this lesson, where students graph the volume quantities of the water in the container and the sugar in the cup, and then the total mass of all of the matter together. Ideally, what happens here is that they analyze the graph and use the understanding that these two columns together, if stacked on one another, would equal the total. Hence, supporting the big idea that the matter is conserved when these two matters are combined, even though the sugar in the water becomes invisible because it dissolves into that water. So small, those particles are so small that they cannot be seen with the naked eye. Another big idea, a big disciplinary core idea that we try to convey through this unit. Here on our sugar and water interaction model and explanation, you'll see that I've created a pretty high-end complex diagram of what's going on with these particles. Now, while I would love to see this out of our students, it's more likely that you'll see some of the features present here. Most importantly, we want to see that students have maintained a liquid model version of the particles. Students may even want to create small keys on their particle models to help their classmates and you as a teacher understand what it is that they are trying to demonstrate. Some students may take it the extra step of creating solid particle caps and solid particle containers, because they are too, of course, solids and matter that are present in this combined model. But most importantly, we want our students to tease out an explanation for why they can no longer see the sugar. And so what they should be able to convey here is that those sugar particles which were previously clumped together in solids, much like the ice cubes from the previous lesson, have now spread out. And they've spread out so much amongst the water in the container that they are no longer visible to our naked eye. This, of course, is embodied in that cross-cutting concept around scale and particles being too small to be seen, phenomena like dissolving happening at a level that's too small to see with the naked eye. Though, of course, when it's the larger chunks early on, we can see that early breakdown. So that's what you're going to want to be pushing with your students. Creating a model that demonstrates what's going on at that level that's too small to be seen, that particle level, and then being able to explain that or support their explanation for their model with what they observed during class, and maybe even supported by some of the graph work as well, with the idea of the mass being conserved, if they can explain that as well.
In conclusion, the sugar cube investigation supports students' movement towards the physical science standard of measuring and graphing the weights of substances before and after a reaction or phase change to provide evidence that regardless of the type of change that occurs when combining substances, the total weight of matter is conserved. It also supports the physical science standard around modeling particles of matter too small to be seen. In this lesson, students are building, using, and revising simple models to describe observed phenomena, as well as collecting data and graphing it in order to draw conclusions from that data. That data should support the argument around the disciplinary core idea that the amount of matter is conserved when it changes form, even when it seems to disappear. This lesson also supports the cross-cutting concept that matter can be conserved even as it flows or changes over the course of an interaction and through a system. This video and associated lesson has been produced by the Burlington, Massachusetts Science Center.